Hi, everybody. Thank you for joining us in the Synthetic Intelligence Forum. My name is Vic, and I'm the founder and the host of this forum. Today, it's my absolute pleasure to welcome back to our forum Professor Warren Powell. Professor Powell is a Professor Emeritus at Princeton University, and today he's going to talk to us about sequential decision analytics, stochastic optimization, and reinforcement learning. Thank you so much for joining us, Professor Powell. It's a pleasure to have you back in the Synthetic Intelligence Forum. The floor is yours, so please take us away.
Thanks, Vic. I always appreciate the invitation. This is my favorite topic. I'm going to talk about what I've been calling the next generation of artificial intelligence. It's my universal framework for sequential decisions. So here's my little background on my background. This is all the projects I've worked on, or at least most of them. I started my career upper left-hand corner in trucking. Truckload trucking was my passion, but I did LTL and parcel. Did about 10 years working with Norfolk Southern Railroad. We're optimizing their locomotives. We've done air freight, mostly with the military. I ran an energy lab for 8 years. Worked in manufacturing and logistics, and these are a fantastic array of problems. Basically, these are the problems of human processes. So when you look at all of these titles, these are all the things that humans are involved in. And in every aspect of them, once you get a human involved, you're going to have humans making decisions. Now, what they're always trying to do is all kinds of goals and objectives. They want to increase profits and reduce costs and maximize productivity, reduce illness, reduce risk. Every time you have a human involved, they're going to want to do something better. They're going to have often one, but usually multiple goals and objectives. Now, anytime you want to improve performance of anything, a supply chain, energy system, health system, you have to make better decisions. So what decisions do you have to make? Amazingly, that's something that not everybody has a quick answer to. And then the issue of how do we make better decisions? So I'm going to start off by reviewing my 7 levels of artificial intelligence, because, of course, everybody thinks that today that you've got to solve all problems with AI. I like to describe 7 levels of artificial intelligence. The first 4 levels are all designed for making computers behave like humans. And in the AI community, it's often thought, boy, if you can make a computer behave just like a human, that's amazing. That's the highest level. Actually, there's 2 more levels that people have been working on to make computers be smarter than humans. And of course, that top level, I sometimes call it fog AI for finger of God, or just science fiction. Level 1, that was 1960s and 70s. This was rule-based AI. If this, then do. If you're eating red meat, then drink red wine. Or if this patient has this set of attributes, use this treatment. Now, the next 3 levels are all some form of machine learning, okay? And I put them at different levels because they do have distinct differences. So level 2 was what I used to call statistics back in when I was starting my career. These are fitting models to data. It can be linear, nonlinear models. We were using early neural networks back then. Level 3 really emerged 2010. This is when we had databases large enough. This was fitting deep neural networks. These are very large neural networks, and they could recognize patterns. And this is where, or voice recognition, this is where we started to say, hey, Siri, and it could do wonderful things. And this was AI, 15 years ago. Now, level 4, this is 2020s, although it really burst out, I think late 2022, early 2023, large language models. This is ChatGPT. Give me a prompt like Jack went to university, and it'll write a whole paragraph or maybe several pages. And this has been the latest version of AI, and everybody thinks, oh my gosh, wow, this is amazing. Now, level 5 is, I'm going to call it deterministic optimization. This has been studied since the 1950s, but it really emerged in the 1990s. Behind all these problems, we have to make decisions. So every one of these boxes has a question where we have to make a decision, and we want to make the best decision. So types of decisions are, we have physical decisions, managing inventory, scheduling nurses, locating facilities. Financial decisions, pricing insurance, managing investment, cash flows, hedging contracts. And then decisions to collect and send and share information, marketing and advertising, running an experiment in the lab or the field, testing drugs. These are all the different types of decisions we can make. Now, there's different time frames: strategic planning, tactical, real-time decisions. So there's all these different time frames and all different levels of the organization. So this could be C-suite, middle management, field operations, could be a truck driver. My point here is when I say the word decision, I mean any decision, any type of decision at any level, any time frame, acting on any type of resource. Now, the basic type of decision-making is called deterministic optimization. Simple example is finding the best path. This is what we do with Google Maps every time. But supply chain may want to locate distribution centers and warehouses and manufacturing. So these are high-dimensional decisions because I have to consider all the permutation combinations where I might put facilities. Now, airline scheduling. So 1990s is when we had the breakthrough where we could apply this basic mathematics of deterministic optimization and then go out to a complex operation like an airline planning for next year, collect data, put it through a package, and out comes an airline schedule. Pretty much every major airline now uses this technology. I want to locate distribution centers and warehouses. So what I'm going to do is set up a mathematical program. I'm going to have variables y. Y is equal to 1 if I turn on the facility at location I, 0 otherwise. Xij is the flows between facilities. I have to model flows to make sure I have the right capacity and to capture the transportation costs. This mathematics is something that, so not everybody recognizes it, but there's thousands of students graduating every year trained in this type of mathematics. And it doesn't matter where you come from. You could be United States, Europe, China. It's one mathematics because everybody speaks the same language, introduced by George Dantzig. Well, George Dantzig was really the person who made this mathematics useful by inventing the simplex algorithm. There are computer packages, some commercial, but a number for free. You can solve nice linear programs even from within a spreadsheet. And lots of talent. If you're a company that needs this skill set, you can market for it. And there's a lot of people out there with this skill set. So let's go to level 6. Level 6 is my favorite topic. I call it sequential decision problems. Now, let's take my set of applications. And earlier I introduced all these different decisions that people make. Now, put your eye on any one box. After we make a decision, information arrives. And this is information that arrives after I've made the decision. Let me go back and do that one more time. So every single one of these boxes, we're making a decision. And after you make a decision, here is information that arrived after I made the decision that's relevant to the decision. These are sequential decision problems. Most decision problems are sequential. You have a decision, then information arrives. Another decision, more information arrives. Every time we make a decision, the information that arrives afterward that hasn't arrived yet is not known when we make the decision. So inventory ordering, I can place an inventory order. It might arrive right away from Amazon, for example, or it may take 7 weeks, maybe several months coming from the Far East. Then I have to make more and more inventory decisions, after which more information comes in about the customer demand. In my company, Optimal Dynamics, this is a startup that licensed software out of my lab. We have the blue circles are drivers. The red squares are loads. We're assigning drivers to loads. But we do this over time because as I'm assigning drivers to loads, then more loads are coming in. And the decision at one point in time has to recognize that it's going to impact decisions made in the future. Wall Street finance, I'm constantly trading assets while the prices are changing. Testing new vaccines. I need to actually try out a new vaccine and then see how people respond to it. So the information is how the population responds, who likes to take the vaccine, the effectiveness of the vaccine. Let's take a very basic problem where I have an asset that I can buy, sell, or hold. And after I buy, sell, or hold, the price goes up, down, or stays the same. And then I have another buy, sell, or hold, and the price changes, and so on and so forth. Now, this is a trivial problem. This is utterly simple. It's a single asset. I only have 3 decisions. The information prices go up, down, or stay the same. And look how quickly it explodes. This is the intrinsic complexity of intermingling decisions with information. Okay, so let's talk about modeling sequential decision problems. If you have any real-world problem and you want to put it and solve it on the computer, you've got to go through the process of a mathematical model. Now, when we have deterministic optimization problems, everybody pretty much knows how to do that. It's a pretty standard skill. It's taught at the undergraduate level. We know how to write out the problem mathematically. By the way, the same is true with machine learning. But with sequential decision problems, it's just not the case. I like to call this the jungle of stochastic optimization. Every one of these terms is a distinct subcommunity that works on sequential decision problems. They each have a book, maybe a whole series of books. The field of optimal control has maybe half dozen to a dozen major books. There's about 8 fundamentally different notational systems. There's a range of techniques, although a lot of overlap. I'm going to show you how to model a sequential decision problem right here on a single PowerPoint slide. We have a state variable. Now, the state variable is information. So inside the academic literature, we've been using the term state variable for about 70 years. And oddly enough, very few of the books actually have a definition of a state variable. In a nutshell, a state variable is information. It's all the information you need at time t to model your system from time t onward. Then you make a decision using the information in the state variable. Then new information arrives that wasn't known at the time that I made the decision. That's why it's index t plus 1. Now, every time I make a decision, I have some performance metric. I might be a contribution that I'm maximizing or a cost that I'm minimizing. It could be a utility function. And it depends, once again, on the information in the state variable and what decision you made. Now, how do we make decisions? We're going to make decisions with a method that we're going to call a policy. And I represent, if I use X as my decision variable, I'm going to say capital X with that superscript pi. Pi is a variable that carries the information that tells me what type of function it is. Now, this function is to be designed later. This is my point of departure with all of those other books in the previous slide. All of those other books already have a method in mind. So they're coming at you with the proverbial hammer looking for the nail. I'm going to sit back and say, relax, we'll get to it later. Let me just put in this function, and it's something magical. You pass it the information, the state variable, and it'll give you a decision. We're good. Now, this thing called the transition function, given that the information in the state variable st, now tell me what decision you made, xt. Finally, now tell me the new information that arrives. The transition function will then update the state variable. State variables can consist of a single equation. It can consist of tens and tens of thousands of equations for big companies like a supply chain or a health system. Now, ultimately, our goal is to find the best policy, the function that works the best in terms of making decisions. Now, I like to list these out as 5 elements: state variables, decision variables, the exogenous information variables, transition function, and objective function. This is the universal modeling framework. This is these 5 elements can model every single one of those problems on the slide to the right. It can model absolutely everything in any of those books. So this is one powerful framework, and we're going to get a lot of leverage out of this because its universality is really tremendous. Now, objective functions for sequential decision problems are a little richer than they are for deterministic optimization. We might maximize cumulative reward. That is, we're maximizing as we go along. We might want to do a bunch of experiments. I don't really care how well I do while I'm doing the experiment. I just want to get the best final decision. And so, and we'll call that the final reward. That is offline learning. We might also need to add a risk term. So a risk term is elements not in my base objective. Usually these are negative events, and almost always they're negative events. Something that I feel like I have to add in an extra term. Now notice in all times, I'm always looking for the best policy. That's very different than the deterministic optimization, where I always want the best decision. With sequential decision problems, you're always looking for the best policy, the best method for making decisions. Now, optimizing over policies, we're going to have this objective function. When we're looking for a policy, we have to specify the type of function that I call little f. That's pretty much always done by a human. We haven't figured out how to get computers to do that. And most of the time, not always, but most of the time, the function has tunable parameters. And usually, we're going to use an algorithm to tune those parameters. So every time I write the letter pi, there's going to be, hey, what type of function are we using to make the decision? And then what are the tunable parameters? Now, how do we evaluate a policy? Well, there's basically three strategies. One is theoretically. And this doesn't happen very often, but for example, in inventory planning, back in 1960, Scarf wrote a paper where he proved mathematically for a particular type of inventory problem what was the structure of the optimal policy, which is when the inventory goes below some level, you order up to another level. These are famously known as SS policies. Now, much more often, we're going to use computers to simulate the policy and then play around and tweak it and find out which policy works best. Now, if you stand back and say in the real world of making decisions, what happens? Well, at the end of the day, we always have to implement the policy in the field. And often we have to choose the policy without the benefits of a computer simulator. So a lot of us are making decisions using some method. No, we haven't written the computer a simulation package to optimize it. Now, I want to emphasize that this bit of not very simple mathematics is exactly what's happening when we go to the field. So at the end of the day, when you test it in the field, this is the objective. And we may not get the optimal policy, but that's what we're going to aspire to. Now, modeling sequential decision problems, I have broken this into a 6-step process. So when you start with some application, step 1, ask 3 questions. What are the performance metrics? What types of decisions are you making? What are the sources of uncertainty? Those are 3 key questions, no mathematics. I cannot build my model without the answers to those 3 questions. Now, if you're playing the game of chess, answering those 3 questions is trivial. It takes a minute. But if you're going out to optimize a supply chain or a health system or an energy system, those questions are actually quite hard. And in fact, recently I've been pushing for training, for example, in business schools, where we have a lot of students who are very business-oriented, maybe not as skilled mathematically as students in engineering and computer science. We need those students who are non-mathematical, but they go to the real problem, but they have to know the right question. And this is what's missing today. We need to teach students how to ask the right question. What are the metrics? What types of decisions are being made? What are the sources of uncertainty? Now, once you have those questions, if the student teams can put that together, now you pass that over to the mathematical modelers. They will have other questions, but they need the answers to those 3 questions. Now, one of the things they will still need to do is to model the uncertainties, and they can do it maybe using historical data, but sometimes we have to build mathematical models. Then we have to design the policies, test them on a computer model. Then we have that process of going back to the field and actually getting people to implement the decisions. Now, if I were to take a supply chain problem, we have all these types of issues. Here's 5 questions. The first 3 involve the 3 questions I asked. What are the performance metrics? What types of decisions? What are the sources of uncertainty? After that, we will need to talk about what information do we need to make a decision, okay? So this is the state variable. And this is a process. You don't just sort of sit down and go, bang, there's the state variable. That's an iterative process that evolves as you discover how to make decisions, design the policy, but also how to model your problem. Now, once you have the state variable, now you have to talk about how the state variable evolves over time. That's the transition function. At this point, we've got everything fully specified. Now, let's talk about performance metrics. It's very common for people to come up with long lists of performance metrics. Here's 3 that I pulled off the internet. And while it's very nice to have these big metrics, it's not very practical, okay, because at the end of the day, you still only have a few decisions. I like the work of Laura Césaire. She's a well-known specialist in supply chain management. She has about 330,000 followers on LinkedIn. Her book, Supply Chain Metrics, no mathematics. This is a book that I credit with analytical thinking. She likes to boil problems down into 2 metrics, inventory turns and operating margins. I like to organize metrics into pyramids. So I recognize that there's many different metrics, and it also depends on where in the company that you're looking at. Like if you're up at the corporate level, you may be very focused on stock prices. Now, below stock price, you'll have operating margins and inventory turns and depreciation, and below that, there'll be more statistics. But organize them in a pyramid so you always understand what's top. But this is only if you're working at the corporate level. What if you're down in manufacturing? Now you may be just, your top metric might be unit costs, and you're focusing on things like labor hours and inventory and downtime, and then so on and so forth. In fact, you may be anywhere in a pyramid in a large organization, maybe down there sort of toward the bottom, and you've got metrics that are unique to your particular role in the company. So in other words, you don't always have to optimize the whole company the way Laura Césaire does. Often we're going into a company and we're optimizing whatever our area of responsibility is. Decisions. Now, I have found that metrics are challenging. They're important. You have to think about them. They're not the hardest thing. Businesses in particular rarely think about metrics, but decisions, those are a lot harder. I'll ask a group of executives in supply chain management, what decisions are they making? I get blank stares. So you have to talk about who's making the decision, because there's different people in the organization. What decisions are being made? And they're made at the strategic, tactical, and real-time execution level. And then what are the decisions doing? Are they acting on physical resources? Are they managing the finances? Are they collecting information? So these are important. I did an exercise. A group of us were invited out for an academic workshop by Amazon. And after the workshop, they took us out to a fulfillment center, gave us a tour around. And I found myself, as I was going around the tour, saying, hey, where are decisions being made? And this is one of the great challenges that I would really ask everybody to think about. Take whatever environment that you're in, whether you're in business or energy or finance or health, and ask yourself, what can I make better, and what are the decisions that I can modify that actually make it better? Because at the end of the day, if you want a better performance, you have to make better decisions. I like this idea of having a decision book. This is a little red book. I got it off of Amazon, and it has blank pages. And the idea is to walk around with it and just always be on the lookout for places where you say, oh my gosh, that's where I made a decision. Now, sources of uncertainty. If you say, take a topic like supply chain management, oh my gosh, they love uncertainty, but they always associate it with risk and resilience. So there's all these books with risk and resilience. It's a very hot topic. Now, risk is always associated with uncertainty. Risk is generally associated with big events that really impact the operation. Uncertainty really does come in many flavors. My contribution to this discussion is chapter 10 of my big book. I have 12 classes of uncertainty. Now, these have nothing to do with any particular area of application. These are all the ways that uncertainty can impact a model or how it's used. And as you go down them, you have to say, okay, well, I'm working in this health area or supply chain or energy area. You have to take your context, go down each of the categories and say, do I have sources of uncertainty in this category? Now, there is some overlap among the categories. Don't worry about this. These categories are just supposed to be an aid to help you say, oh, yeah, I do have that type of uncertainty. Like one of my favorite is communication errors. I had a friend who was working in supply chain management, and they nearly had a major meltdown because of a communication problem. There's also implementation errors where they don't do what they're told. So people overlook that. Goal uncertainty. Somebody from working in industry came back and says, oh my gosh, you got to put in goal uncertainty because different people have different goals. And we're not always certain about what their goals are. So these were all major sources of uncertainty. Now, there's different styles of uncertainty, hourly and daily variations demands, bursts and spikes. This came from, once again, from Amazon. They told me in their fulfillment centers that 98% of the items on any given day have a demand of 0. And I was thinking, demand of 0, that shouldn't be too hard to stock. You just put one item, and then when a demand comes in, you sell it, and then vanishes for a long time and I can restock. That's not how it works. What'll happen is one person buys something and they get it and they tell two friends and they tell two friends, and you get this little burst and you get this flurry of sales, and then it just goes away again. And what kills you is the fact that when that demand happens, you're going to then get a flurry, and if you don't have enough inventory in stock, you're going to lose out on those demands. You're going to have periods where you go to elevated plateaus and you move to shift to whole new areas. Here's one of my favorites, Bud Light. Bud Light was churning along as the top light beer, and somebody in marketing came up with a great idea of having an LGBTQ ad series to reach out to that community. Well, that didn't go well. Apparently, Bud Light has a lot of drinkers that have very strong opinions. They lost 25% of their market share in just a couple of months. And, that just kills a supply chain. You've got your black swan events. Think of this as a self-induced black swan event. And you may want to do contingencies for events that haven't even happened, but you're saying, yeah, but they could. Now, designing policies. So let's get to the process of actually making decisions. First of all, what's a policy? I get this question all the time. A policy is a method that makes a decision using the information in the state variable. And I mean any method, because there's a surprising amount of confusion for this. I'm up to about 48 different words in the English language, each of which in the right context mean a policy. These are all words that say, or effectively say how to behave, what decisions to make. Now, I want to bridge between machine learning and sequential decisions. Machine learning is all about finding functions. We call them statistical models. Sequential decisions is all about finding functions. We call them policies. With machine learning, I have to have a training data set. So I have a generic function X. It could be a linear function or nonlinear. It could be a neural network. It's some generic function. And it has tunable parameters. It could have one or two tunable parameters. Deep neural networks, I think the large language models have hit 1 trillion tunable parameters. But in the millions is very common. And you use the training data set, hopefully it's a big training data set, to fit that function. Now, sequential decisions, we do not use a training data set. We do not have a generic function. We have a policy. We have to specify the objective function, the cost and rewards. We have to specify the transition function, which is where all the dynamics and the physics of the problem lie. So this is where they're different. Both of them are searching over functions. So, but the sequential decision side, we have to tell it about the problem. Now, how do we search over policies? So there are two fundamental meta strategies for designing policies. The first is what I call policy search, where we search over a function to find the function that works the best. The second builds functions by planning into the future. Each of these can be further divided into two subclasses. Let's start with the first one. So the first of these I call policy function approximations, or PFAs. This could be a rule like in inventory planning, when the inventory goes below some level, order up to another level. In finance, it could be buy low, sell high. It could be when it's cold, wear a coat. It could be a linear model. It can be a neural network. It can be any function that you might use in machine learning. This is the only one of the classes of policies that does not require solving an embedded optimization problem. So the second class, policy, is I call cost function approximations. This is a term that I've introduced. Oddly enough, this is widely used in industry. This is where you take usually a deterministic approximation of the problem and optimize it, but then you put in some tunable parameters to make it work better over time under uncertainty. So when we are trying to find the best path to a destination, and let's say I'm traveling there, either every day for work, or maybe it's a new company that I'm visiting, and I'll be driving there from time to time. I'll use Google Maps to find the shortest path, but I still have the decision of how much time to allow. So Google Maps may say, oh, yes, it takes you 40 minutes. And I'll go, oh, yeah, but because of traffic, I'm going to allow an extra 15. And after you do it a few times, you say, wow, I don't really need to allow 15. I'll adjust it back to 10. So that buffer that you've added in is the tunable parameter. Maybe I'm scheduling nurses for a hospital. I might want to schedule them for 32 hours a week, even though they work 40 hours a week, because I know that random stuff comes up and I've got to have some slack in the schedule. Airlines do this when they schedule airlines. They put in slack for weather delays. Here's something, advertising a product. I may have an estimated revenue, but the estimate may not be very good, and I may have had some bad luck. So I'm going to add in a bonus term, the standard deviation times some tunable parameter theta, and I have to find the value of theta that makes it work the best. Each one of these has a simple, let's say, deterministic optimization problem. They each have tunable parameters. This is widely used in practice. What's been missing is a recognition that the parameter tuning is itself a stochastic optimization problem. Here's an example, optimal learning. Let's say I market 7 products, 4 baby products, 2 kitchen products. And by the way, I have something called correlated beliefs because I have some people who like my baby products, other people like my kitchen products. And so there's a higher correlation. So if I try selling one of the baby products and it, sells better than expected, maybe that means my other products will sell better than expected. So here I am. Here's my 7 products, and maybe I test market product G, and I get higher sales. I'm like, wow, that's pretty good. I'm going to have to update my belief about product G. Because of the correlated beliefs, I can actually update everything a little bit. Okay, so this is very useful. How do I choose which product to market next? And so these are I'm showing you some actual methods used by e-commerce giants like Google and Facebook. Upper confidence bounding, interval estimation, Thompson sampling. Think of these as 3 functions that earlier I called little f. Now, each one, I have a point estimate. This is how well I think product X is going to work. And if I had a lot of confidence, I would just go with that and pick whichever one is the best. Now, each one handles uncertainty in a different way, and I have an uncertainty metric. And then I multiply that times a tunable parameter, add those together, and then find the biggest one. So these are optimization problems. They're not very hard optimization problems because it's a sort. I had to just find which one has the biggest term in the parameters called an index. Let me illustrate interval estimation because this has been one of my favorite. So if I pick set the tunable parameter at 0, that means what I'm doing is just taking my point estimate. I'm looking at, and hey, product E, my best estimate is product E has the highest revenue. I'm just going to go market with that. Now, if I put the tunable parameter equal to 2, now I'm going up on the upper tail and I'm saying, oh, well, I've got a lot of uncertainty about product G. That one might be the best. Now, product G also might be the worst, but we're going to go with some theory that says, hey, let's be optimistic. Now, what I want to be able to do is to find the best value of theta. Now, over on the right is a graph that plots opportunity cost. Smaller is better. So I want to find the value of theta. It's the smallest. If I set that theta equal to 0, I get a very bad response. It's not good to go with the point estimate. It's good to be somewhat optimistic because I might just be unlucky. I have a bad estimate. If I just never try that product again, that's just not going to work well for me. Now, I have another method, a much fancier method, not one of the 3 that I just showed you, that we call the knowledge gradient. I'm very proud of this. This came out of my lab. I had about 8 different students work on this. Notice that it doesn't have a tunable parameter. It just works at a certain level, works pretty well. It comes out at a pretty low opportunity cost. Very interestingly, if you properly tune interval estimation, it actually will work even better. Now, this blew me away the first time I saw it. The student presents the table, and I'm going, wait a minute, what's going on? Interval estimation, which is a very simple policy, you can easily code it up in a spreadsheet, is outperforming. The lesson here is that a well-designed policy, properly parameterized, can work much better, can at least work very well if it's properly tuned. Here's the hard part. Tuning is hard. That opportunity cost curve is very hard to compute. It requires simulating a policy, and simulating policies is very noisy. So lesson here is simple rules are great. Everybody likes simple. The price of simplicity is tunable parameters, and tuning's hard. Here's another cost function approximation. I'm trying to ship product around. I have to find the best suppliers to buy my product, but I've got various types of uncertainties in market behavior, supplier uncertainty, and product quality. Here's my basic deterministic linear program that would optimize where I buy my parts, but because of my different types of uncertainty, I'm going to put in some tunable parameters. I still have a simple linear program. It's still just as easy to solve. The hard part is fixing those parameters. Industry takes this approach all the time. Often they don't do a very good job of the tuning. They're sort of reaching up and grabbing what seems to be a reasonable number. Now, what you can do is, here's my policy. It is a deterministic linear program. A lot of people mistakenly say, oh, my policy is to solve this deterministic LP. Therefore, I'm using deterministic optimization. I'm not doing stochastic optimization. Now, what you need to do is to simulate your policy. I'd like to simulate it in the computer. Now, that means somebody has built a simulator. If you're not going to simulate in the computer, I can tell you where you are going to simulate it. It's in the real world. But that middle line means I evaluate the policy using simulation, whether it's in the computer or the field. But now I'd like to do tuning. And this is where you're doing stochastic optimization. Even if it's a little ad hoc, I think this is a good parameter. That's where you're doing stochastic optimization. So if you're solving problems under uncertainty, it's unavoidable. You can't say, oh, I'm not using stochastic optimization. It's too complicated. Yes, you are using stochastic optimization. You're making decisions under uncertainty. You're doing the best you can. CFAs are widely used in industry, airlines optimizing their schedules, manufacturers using buffer stocks, optimizing location of distribution centers. You've got to you've got to put your centers to anticipate the different types of uncertainties. Grid operators. This is the people who plan energy generation. This is where I got the idea from, because this is exactly what they did. And even though they didn't have a simulator to tune their buffers, they had to anticipate that generators may fail, and they had to make sure that they would never have a power outage if one of their generators failed. So I actually have a web page, tinyurl.com/CFA policy. It's a web page dedicated to explaining cost function approximations. By the way, here's my problem of locating distribution centers. We think of that as a static problem. Everybody solves a static problem, but it's not. It's a sequential problem. I'm solving those every 3 months, every year. I'm having to make decisions now anticipating the impact. This is something that we haven't been teaching students, and we need to do that. Now, so what this means is when you go to solve that optimization problem, you're not just solving it once, you're solving it at a point in time. You're going to repeatedly solve it, which means it's a policy. And the optimal solution is a decision that you're making at a point in time by making that. Probably I've put in some tunable parameters to say, well, I'm not exactly sure what demands there are. I have to make sure that I have enough capacity in all the facilities. Now, of course, we have to simulate that policy over time. That bottom line, there's your stochastic optimization problem. And if you're not doing that, that would have to be done in a computer. But if you're not going to do it in the computer, then you are doing it in the field. PFAs and CFAs both have tunable parameters. They generally require running some sort of a simulation, once again, in the computer or in the field. And these simulations are noisy, and that's what makes this hard. So this is its own sequential decision problem. I can use derivative-based stochastic search. I can do derivative-free stochastic search. Both of these are their own sequential decision problems. So let's go to the second class of policies, the Lookahead approximations. Now, Lookahead approximations, here I have Dorothy in the Wizard of Oz trying to plan her path to Oz so she can get home. She has to decide what to go. The way she's going to make that decision is by thinking about the future. She's not just going to look at the immediate decision. She has to look downstream. Now, the way to look at this mathematically, it looks pretty frightening. This is the immediate cost or contribution of a decision, and this is the downstream impact. And yes, that looks frightening. And a lot of times in a business community, you may say, take one look at that and go, oh my God, that's just impossible. I can't possibly do that. No. All of us humans will approximate this in some way. And one way to look at this is as a decision tree. So let's say you're at a particular state and I have to make a decision. Now, this shows one of three decisions, but X can be, hey, what possible combination of warehouses and distribution centers? This could be very high dimensional. I want to make the best decision, but I have to realize that after I make the decision, something random might happen. That first expectation is averaging over the randomness that happens immediately after I make the decision X. And then in the brackets, I have all that other stuff about the future. It involves those square boxes. For every square box, I'm making a decision. And to make that decision, I'm going to need another policy. I call this the policy within the policy, because this whole look ahead is a policy, but I have to anticipate decisions I might make in the future. And then, of course, I have other types of uncertainties. Now, if you're saying, holy smokes, does this seem complicated? It is. I can't compute it. So there's two strategies. One is to say, once I make that first decision, I've got this function that all depends on the downstream state as t plus 1. Why don't I just call this a function, a value function, which is a function of the state I'm in after I make my decision, also after that first bit of randomness happens. There's a whole field of research called Markov decision processes. It's been studied since the 1950s. Its foundations is Richard Bellman. The bad news is it's not really computable unless you have some toy problem. It's amazing how many years we have continued work on this. Another whole approach is to do some sort of approximation. This is generally known as approximate dynamic programming. Computer scientists will call it reinforcement learning. Notice that I've been able to get rid of the expectation using something called a post-decision state variable. If I approximate the value function in a convenient way, X can even be a high-dimensional vector. Here's an example. My company, Optimal Dynamics, assigns drivers to loads. We might have hundreds to thousands of drivers and loads, and I have to make these decisions over time. And as I'm stepping forward in time, my decisions on Monday, I have to anticipate that they impact what happens on Tuesday and Wednesday. Now, what I'm going to do is I'm going to come up with approximations of the value of drivers landing at various locations. It's an approximation, but it's better than nothing. This is very easy to solve. In fact, so easy that the blue parts of this picture can be solved in often a fraction of a second to maybe a couple of seconds. It's so fast that I can simulate it forward in time, and I can run repeated simulations, and it's during these repeated simulations that I learn the downstream values. Now, here's experiments run on 11 different trucking companies. Here at the beginning, I said, let's just anchor everybody to this base value when all the future values are zero. So if I ignore the downstream impact of the value of a driver in the future, this is what I get. Now, after I've done the training, I get improvements of 10 to 50%, which is quite nice. So in other words, if I ignore the downstream impact, I'm really underperforming, so much so that I can tell you that even people in the field will be able to say, wait a minute, this recommendation doesn't make any sense. You're sending drivers into Florida. I know that there's no loads in Florida. So unless I'm making a very large amount of money, I can't do that. Or maybe they're getting stuck out in Montana. Dispatchers without fancy educations will be able to realize that if you ignore the downstream impact, you're getting yourself into trouble. We've been able to build this technology and build everywhere from highly detailed strategic simulations to actual real-time dispatch. We've got companies out there that are now implementing close to 100% of our recommendations. Now, the very last of the four classes of policies are direct look-aheads. I like to say that this is what we do when all else fails. Guess what? All else often fails. So what we're going to do is we're going to have a base model. We can call that a simulator. We can call it the real world. I'm going to then build a look-ahead model. This is where I'm planning into the future. But notice how I put tildes on everything. That's because I'm going to plan ahead approximately. I'm going to simplify my state variables and decision variables. Notice that all those variables have two time indices. So I'm planning into the future at a point in time t, here and now, into the future at some time t prime. So all of those look aheads are all indexed by t over a series of time periods into the future. Now, what we're going to do is we have to build an approximate look-ahead model. Now, this is an art form. You have to have an understanding of what's important to capture, as well as how hard it is to compute. So what I need to do is I'm accepting that if I don't do any simplifications, I won't be able to compute that. So I have to be able to identify the types of approximations that I think will be computable, but I'll still be capturing what's important about the problem. And I wish there was a simple formula for that, and it's not. I have a whole discussion of this in my book in chapter 19. Now, let's assume that you were able to come up with a reasonable approximation. I'm going to look forward, solve the problem, make a decision now, roll forward, update everything, solve the problem, make a decision, roll forward, update, so on and so forth. Now, a good example of look-ahead policies is Google Maps. Here I am in Hartford, Connecticut, upper right-hand corner, trying to get home to my home in Princeton, lower left-hand corner. It's 4 o'clock in the afternoon, and Google Maps uses a deterministic look-ahead. So the first approximation it's making is it's saying, let's get rid of uncertainty. So now I'm just solving a shortest path problem using point estimates. The optimal control people call this model predictive control. So let me just tell you, any decision based on modeling into the future is a form of model predictive control. But the optimal control people almost always equate this with a deterministic look-ahead. Now look at what Google did. It planned a path right through New York City at 5 o'clock in the afternoon. And I'm looking at this going, Google, you can't possibly be serious. I mean, that could be terrible. Now, what I'm doing is saying, it looks like Google's saying that that'll be okay, but I know that it might be bad. I'm using an idea called robust optimization. I'm saying, what decision would I be making given sort of the worst that might happen? Well, Google tells me of an alternate route. It's only 5 minutes longer, but now I eliminate the risk of possibly getting stuck in New York City traffic. Now, there's entire books written about different ways of modeling in the future. Stochastic programming, approximate dynamic programming could be one way. Entire books on different ways to model into the future. Now, I have described 4 classes of policies. The first 2 are the simplest, the policy search classes, the PFAs and the CFAs. The second 2 are more sophisticated. These are the look-ahead classes where I have to approximate in some way the value going in the future. Now I'm going to make a very strong claim. These 4 classes are universal. They include any method that you might use for making a decision, whether it's in the academic literature or used in practice. These are meta classes, so it even includes methods that haven't been invented yet. So this is very helpful because it allows you, instead of getting locked into one of the types, which is what's very common, I can sit back and say, what's best for my problem? So here's an example that I really like. It's a nice energy storage problem. I'm getting energy from a wind farm. Of course, the wind fluctuates up and down. Or I'm getting energy from the grid and the prices are going crazy. Although I can always get infinite supply from the grid, I have to pay random prices. I need to meet a demand, and I've got a Tesla Megapack to help absorb the variations. Now, one of the problems with energy from wind, it is highly variable and not very predictable. This is a 24-hour period. It's real data. The black line is the actual energy from wind that we realize by the end of the day. The various lines, that first line is the forecast as of midnight, and the remaining lines are the updated forecast over the course of the day. So we realize that the forecast really changes. This is rolling forecast. It means the forecast itself. If I sit at midnight, I can't even say that I know what the forecast for 4 p.m. would be at 8 a.m. So the forecast itself is random. I actually worked on this for quite a while, ended up settling back on a good old deterministic look-ahead. Now, buried in that deterministic look-ahead is the forecast. Now, I know that forecast is not very good. So how do you deal with the uncertainty in that forecast? So guess what I tried? I put in a discount factor. Now, this doesn't sound very fancy, but what I did is this is a discount factor, depends on how far into the future. So you have t, it's indexed by t prime minus t. So for my 24-hour horizon, I've got 24 of these for 1 hour out, 2 hours out, up to 24 hours out. Now I have a parameterized deterministic linear program. This is not the only way to parameterize it. Maybe somebody else would have some different ideas. So I have different ways of parameterizing. But for this parameterization, now I have the challenge of choosing theta. Now, what I'm going to do is, once I've picked theta, I have a simple linear program, very easy to solve in the field. So I can keep rolling forward, just like Google Maps, take the updated data, re-optimize, very easy to implement in the field. I'm going to use a process very similar to what I did before. My Lookahead policy is a deterministic linear program. The objective function involves simulating that policy. This gives me a stochastic optimization problem of choosing both the best parameterization F and the best parameters theta. For this project, we use a stochastic gradient algorithm by Jim Spall, his SPSA algorithm. Now, what we did is we ran two sets of experiments. The first one, we said, you know what, just as a test, let's set up experiments where the forecasts are actually perfect, okay? And we're not going to tell the algorithm. Guess what? The algorithm came back and says, wow, the best value of thetas, all the thetas, is 1, which is just what I would expect and certainly hoped for. So that was very reassuring, that if I have a perfect forecast, it's going to come back and say, sure, theta is equal to 1. But when you put in the more realistic data, now we've got these thetas that when optimized. So the theta 2, 3, 4, and 5 hours out, that's those top 4 lines. Now I want a theta somewhere between 0.2 and 0.4. That next blue line, that's the 1 hour out. I don't really entirely understand that. But it's saying, okay, well, maybe I want a theta more like 0.7 and the rest sort of all over the place. What do I get by doing this? So if this baseline, here's a whole bunch of runs of different problems. If I just set theta equal to 1, I get that base. If I optimize theta, I get about a 30% improvement. Now, I don't know if that's optimal, but it's a lot better and it's practical and implementable. So again, this is one of these ideas. I got by watching what industry was doing and I said, oh, this is a great idea. They don't think they're doing stochastic optimization. Of course they're doing stochastic optimization. They just needed fancy words and fancy math, and so that's what I gave them. So we actually took this same energy problem and created 5 variations of it. Then we created 5 different versions of policies, one from each of the 4 classes, plus the hybrid. That's the hybrid I just showed you. We made each of these 5 policies work best on one of the variations. So this is one reason why I think that we need to be aware of all 4 classes. Now let's go back to my bridge between machine learning and sequential decisions. The PFAs are actually any function that you use in machine learning, you could use as a PFA. If all you did was limit yourself to PFAs, you're doing almost the same thing as machine learning. The difference is I'm not using a training data set. I have to use a model of the problem. But I've got those other 3 classes of policies, which, by the way, is how I address high-dimensional problems, because now each of the one involves an embedded optimization problem. In real applications, most of the time, that optimization problem is just a sort, but it could be a big integer program. So this is what allows me to scale to these big problems today. Now, when we look at all these books that do stochastic optimization, let's take a look at these. Of these, 10 of them really focus in sometimes exclusively or sometimes they prominently represent methods based on Bellman's equation. The optimal control people will call it Hamilton-Jacobi equations. Academics just love Bellman's equation, okay? It's very hard to solve. Now, if they're not using Bellman, they like lookaheads, especially stochastic lookaheads. There is some attention being given to PFAs. You won't find any mention of cost function approximations. It's simply not there. Let's take the 4 classes. I'm going to take the 4th class and split it into 2, deterministic lookaheads and stochastic lookaheads, because I think those are 2 very important subclasses. I now have 5 types of policies. Let's sit back and do something which none of those other books are doing and say, which of these are most useful? Well, here's what I came up with. I decided these category 1 includes PFAs, CFAs, and deterministic DLAs. These are the big 3. If you were to stand back and say, look at all the decisions anybody makes, how did they make the decisions? I would probably suggest 97% are made with the policies in category 1. This is what we should be teaching to our younger students. This is what's most useful. Even if people don't do math, they should know that they're there. They should be able to understand, well, yes, maybe this is a good opportunity for a PFA or a CFA. We humans seem to evolve the ability to use these 3 classes, and we barely even know that we're using it. We do it just so naturally. We don't even think of it as a method. The only people that have to think about them are people like me, where we have to code them on the computer. And so we have to say, okay, wait a minute, how do I actually code that? Now, category 2, I put by itself, this is stochastic lookahead. This is where you're saying, this was me saying, here's the shortest path from Hartford going through New York City. It might be bad. Because it might be bad, I'm going to go a different route that reduces that risk. I think there's actually quite a few times that we realize that we're looking out and then we see something bad that could happen. So I put that as category 2. I put VFAs all the way down in category 3. I need to remind everybody I wrote a 500-page book and spent 20 years of my life on VFAs, like every other academic. So I am one of the masters of approximate dynamic programming. I have applied them in so many problems, and they are being used at my company, Optimal Dynamics. But in the universe of decision problems, this is for very special cases. It's a very complex strategy. Getting value function approximations to work is hard. I would really limit it to PhDs. You need experience. Do not trust anybody who says, oh, yes, here's my reinforcement learning algorithm. I can just run this and it'll work. No, it just won't. When you get down to an actual real-world problem, you're going to learn how hard it is to get those techniques to actually work. Okay, let me now compare machine learning to those parameterized policies, the PFAs and CFAs. Deterministic DLAs don't have to be parameterized, but we can, because I illustrated one. When we're doing machine learning, we search over functions, and then we have to tune the parameters using the training data set. When we do parameterized policies, I have different functions. A human has to choose among them. We even have to choose within those. And then an algorithm has to do the parameter tuning. When you limit yourself to these parameterized policies, which is what is most useful, this starts to look very much like machine learning. So I'm going to close my talk with a pitch for a new educational field. Optimization, well-established field, lots of books, standard vocabulary, packages you can use. Machine learning or statistics, the same thing. A lot of books teaching roughly the same material. There's a lot of computer packages, a lot of people learning this. By the way, simulation, Monte Carlo simulation, a little bit more specialized, but once again, a bunch of books. Simulation doesn't have so much packages because you sort of have to program it, but it is still a very important tool. Then we get to sequential decision problems. And this is a mess. We don't have standard books. We don't have standard methods. The mathematics is complicated. The theoreticians seem to come out of the woodwork. And so I don't consider myself a theoretician. I wrote the book in the upper right-hand corner. But these are hard techniques. Now, I've written a series of books. The first one is, I call it my big book. It appeared in 2022. I gave it the name Reinforcement Learning and Stochastic Optimization. It's the first book entirely written around the framework that I've given in this talk. It's graduate level, primarily PhD, but I would say a master's student from an analytically sophisticated field, operations research, computer science, electrical engineering, could use this. It's written for an engineering audience. I taught this course at Princeton. I had students from 8 different engineering departments, but pretty much all grad level. I actually had a couple undergrads. I have another book that I wrote for undergraduates, and this can be downloaded from the internet. So far, it's had about 14,000 downloads. It uses a teach-by-example style. With the exception of chapters 1 and 7, every chapter is on a different application, following the different style, the same outline, and illustrating the notation. So this is for an audience that is comfortable with notation, wants to see modeling in different contexts. It's almost a case studies for mathematical modeling. I have a third book. This book has been written for instructors. It's very short. It's not a textbook you can show to students. It's for people teaching introductory to optimization, usually an introduction to linear programming, either at undergraduate or master's level. And for the people who think that if you teach optimization, you have to teach linear programming in the simplex method, I've got a different idea. I break optimization. First of all, I interpret optimization as intelligent decision-making, so much broader. I break it down into 11 topics. I don't get to linear programming until topic 11. Topics 1 through 6, I start with machine learning. Topics 2 through 5 are various types of sequential decisions based on examples from the previous book. Topics 7 through 11, I do linear programming, integer programming, and nonlinear programming, each one taught both as a static problem and then as a sequential problem. I really don't use Bellman's equation anywhere. This is designed for an introductory audience. I teach linear programming 3 different ways. The first one with no mathematics. It's just like, here's what a linear program is. The second way I teach using a network problem, no mathematics, but I teach the simplex with a picture. And the third way, I do the network problem with the linear algebra. I have a web page, tinyurl.com, RLSO courses, that shows you how to teach this material to yourself. I have an introductory seminar built around my undergraduate level book. I have an advanced seminar. These are seminars are ones where I anticipate a group of students getting together, meeting for lunch once a week, and one student stands up. For the advanced seminar, I tell you specifically what sections within the big book. The introductory seminar, I pretty much say just follow the introductory book. I also have a second one for this is the new way to teach optimization. So I've mentioned a few links. You actually only need to remember one link, which is this one, tinyurl.com/SDA links. This is a web page of links. So it's a resources web page with books, videos, educational web pages, courses and teaching methods, and there is a link to a series of educational LinkedIn posts. I recommend that you follow me on LinkedIn. I'm posting every week with new ideas. Thank you very much.
Thank you, Professor Powell. It was a very thoughtful and thought-provoking talk, and a lot of questions come to mind, but perhaps the one that really resonated with me when you got to the slide around you talked about policy function approximation, cost function approximation. You talked about direct lookaheads, value function approximation. And at one point, you talked about hybrids, or we can think about them as ensemble methods. So can you talk about, given that each of these methods or classes of policies have different costs and requirements, but they also surface different types of insights or differently surface various insights, what's the right way to sort of think about them collectively rather than individually?
Okay, so first of all, if you go to this links, there will be a link to my big book. And so although I don't allow people to download the whole big book, I do allow you to download some key chapters. Chapter 9, which is how to model, and Chapter 11, which is dedicated to a discussion of all 4 classes of policies. Go to section 11.10. First of all, this is where I will talk about soft issues. So when I talk about what's the best policy, in the real world, you're not always looking for the best policy. You want policies that'll be reliable. Transparency can be an important issue. You may want to know that when it gives you a decision and you're scratching your head going, wow, I don't understand that decision. You might want to know, well, how dependent is on data that I may not trust. Complexity. Maybe you're in a decision analytics group where you have to program this policy. Well, like value function approximations, I'm going to tell everybody up front, this is not easy stuff to get working. So if you want to go down the road of a value function approximation, you need to have a good feeling that that really is the right way to go. Okay, so I spent a lot of time in my academic career, but that's what I'm supposed to do as an academic. If you're in a company where you're saying, look, how long is it going to take to get this running? And you're scratching your head going, wow, I don't know. That's a problem. You may want to go with something simpler. There's trade-offs in the CPU time. So I haven't even gotten to the issue of hybrids. Now, in Chapter 11, I also have a section on hybrids toward the end. And that's where I list a variety of different hybrids of mixing and matching. And by the way, we humans use hybrids all the time. Think of playing chess, where we're saying, okay, if I do this move, my opponent may do this move. And I'm a pretty bright guy, but I'm not one of these people who can think 10 moves in the future. I might be able to think out 3 or 4 moves. And then I'm like, okay, wow, at that point, I've lost my queen. And, at that point, you truncate and you're basically using something like a value function approximation. And if I'm dispatching trucks, I may say, well, if I send this truck to Minnesota, well, after that, he can go to Texas. And after that, I don't know what's going to happen. But Texas is a pretty good place to be. That's me doing a hybrid of a look ahead with a value function approximation. There's a number of ways to do two classes at the same time, sometimes 3. I even supervise some research where we try to use all 4 classes all at the same time. So it's a very rich topic. When we do deterministic optimization, we always want the optimal solution. But when we do sequential, we're looking for methods. And as much as I say that I want the best method, it's more complicated.
Thank you for that, Professor Powell. Perhaps the last question I have is going back to the start of the talk. We talked about the notion of policies and how important states are, because that's where we start. We make a decision, information comes in, we make the next decision, new information comes in, contributions are made. So, Professor Powell, how do you account for partial observability of states, and especially when what is being partially observed can potentially change across different decision steps at different time steps?
Okay, so first of all, partial observability, this has to do with belief states. So I like to divide state variables into 3 categories. The first one I call R for physical state, resources, inventories, location of a truck, where are the facilities type of thing. The second one I call I for information, because it's pretty much anything that I know that's not a resource. But the third one is beliefs. I call that B. So you can have sequential learning problems where the only state variable is a belief, but you can also have other problems where you have mixtures of, hey, I've got a drone moving around. I know where the drone is, and he's trying to learn the environment, which I don't know perfectly. Okay, so you have a mixture of a physical state that I do know, and he's learning the state of the environment, which I don't know perfectly, and so I have a belief about it. Putting beliefs in state variables is one of the most subtle modeling constructs. It's been widely studied under banners like multi-arm bandit problems that have a mixture of physical state and belief state is not widely studied. I have a web page where I put 2 papers, both of which involve managing a physical resource. One's a drone, one's a utility truck after a storm. And it has belief states like after the storm, I don't know where outages are, and I have to have a utility truck running around discovering that. This is a very rich area. It's very subtle. Both of those papers, I tried to get published, and we couldn't find referees who knew how to read them. So I just decided to publish them on a web page. I ran into COVID issues and said, okay, I just don't have time to deal with this. And, it's a very subtle topic, and I can set up problems where you can have a shortest path problem. By the way, shortest path problem is one of those problems where everybody uses Bellman's equation. It's just, what's the value of being at a node? It's a physical state. And then you can take one of my pure learning problems where the state is what you believe. I can also set it up with Bellman's equation. Now, nobody uses Bellman's equation for belief problems, but you can. And Chapter 7 of my big book does show you how to do it. In fact, Chapter 7 takes pure learning problems where there's nothing but a belief state, and it illustrates all 4 classes of models just for a problem where the only state variable is a belief state. Very rich topic.
Thank you, Professor Powell. That brings us to the close of this episode of the Synthetic Intelligence Forum. Thank you so much for joining us, and we'd love to have you back, and we hope you'd come back when there's more updates to share with our community. But on behalf of the forum, I really want to express our appreciation and gratitude.
Thanks so much to everyone, and please share this information as widely as possible. This is where I'm spending my retirement, is to get this message out.
Thank you.